generation BeiDou MEO satellites. Quick outline of the talk. I'm going to tell a little bit about the spacecraft dimensions, the underlying processing strategy that we applied, then present some results, Pseudorange data quality, the quality of the orbit and clock estimates, also report about solar radiation pressure estimates and about the antenna offsets that we have estimated in this first attempt. So quick overview about how the satellite constellation has evolved over time. As we heard this morning, the third generation BeiDou system development has started in 2015 with the launch of the first 5 experimental satellites. Then in 2017, 16 non-experimental MEO satellites have been launched between November and October 2018. Those satellites have been launched into all 3 MEO planes, and what's interesting is that they are built by different manufacturers. There are currently 8 satellites that have been built by the Chinese Academy of Space Technology, CAST, and another 8 satellites built by the Shanghai Engineering Center for Microsatellites, SECM. These satellites are still in orbit testing, so not fully operational yet, but they are still transmitting a legacy B1 open service signal, and that signal is being tracked by quite a growing number of IGS sites at the moment, about, you see that in the plot over there, up to 70, 80 sites per day. And that was actually the motivation for us to try first orbit determination using these IGS sites. A bit about the spacecraft dimensions. The new satellites are really fundamentally different to the previous generation of MEO satellites. They are much lighter, also less cuboid as the second generation. The shape of the main body axis, the X and the Z axis, is about 2 to 1. And what we've tried here is we estimated basically the effect this varying cross-section of the spacecraft body has as on here SRP modeling, to see how much this would impact our SRP modeling and the orbit determination. This is very simple, just computed the difference between the maximum and the minimum radiated area of the bus, divided it by the mass. That gives you kind of an impact factor, kind of sensitivity impact factor, if you want. And we did that for different kind of satellites, also for the second generation MEOs, for Galileo, QZSS, and so on. And in blue are the 2 different type of BeiDou 3 satellites, and here we end up with a factor of 1.9, 1.6, which is higher as the BeiDou 2 MEOs, but still moderate, I would say, compared to other GNSS satellites. For instance, QZSS gets a 5.7, also Galileo is obviously much more sensitive with a 3.4 factor. So, yeah. A bit about the processing strategy that we applied. So we processed daily batches, 24-hour arcs with latest NAPEO software, 11 months of data, and it's basically a 2-step approach. We first do POD for the GPS constellation with the same setup and same models we use for operational IGS processing, and then a follow-up BeiDou solution in which we estimate the BeiDou satellite orbits and clocks and hold the other parameters fixed. Take them from GPS. Also, very simple orbit model that we use, basically two parameters, purely empirical, without any background model, just a D0 term and constant A0, long track CPR term. And yeah, the ionosphere is of course a big issue here because we don't have dual frequency data, so we simply average the B1 phase and pseudorange observables, well known as the graphic method, to get rid of the ionosphere. And then finally, to estimate the satellite antenna offsets, we combine the daily necks into one neck file, then we are able to resolve for the antenna offsets. A bit about the data quality of these observables. Compared to BDS2 MEOs, the residuals are much lower. The residual RMS for these 16 satellites was about 0.14 meters, so very, very small RMS, which is 40% smaller as for BDS2 MEOs. I also computed here with TQC basically the multipath metrics for a couple of station receivers which provide dual frequency data. And there again you see for BeiDou 2, this is green, and BeiDou 3 is in blue. The residuals are much lower, actually up to 50% lower RMS, and also for the other signals as well. Yeah, the overlap residuals, so we have, as I said, we have daily arcs, and we compare basically the overlap at the midnight epoch. Do that for the orbits, so also did that for the clocks. So we measure for the consistency, and that gave a total RMS for the orbit overlaps of approximately 1 meter, and for the clocks for approximately 0.7 meter. Most uncertain component is, of course, the long track component with 0.9 meter, and yeah, that's roughly what we have expected since we don't have a proper network yet and just single frequency data. And also interesting to mention that there's no really difference between the two type of satellites. The cast-built satellites and the SCCM satellites the orbits are of similar quality. And we also compared our estimated orbit against the broadcast orbits that gave an agreement of 1.4 meter in terms of 3D RMS. Here you have to account for the different reference points, of course. Our ESOC orbits, they refer to the center of mass. Broadcast orbits refer to antenna phase center. And apparently this has been changed, or the change, you see that in this time series around April. The system operators have apparently switched from center of mass coordinates to antenna phase center coordinates. And so what I did was I computed the mean difference between ESOC orbits and broadcast orbits after April, and that gives you a rough estimate of the applied Z offset. And that's in the order of approximately 1 meter, 1.3 meter, depending on satellite type. Okay. Then SLR residuals, there are also SLR residuals, so SLR data is available meanwhile for 4 satellites, which are tracked by 18 ILS sites. That gave a total RMS of 0.14 meters, which is pretty good, I think. And what's interesting here, what I did here is I just not only compared our orbits, the ESOC orbits, they are shown in blue, the SLR residuals of the ESOC orbits, also the broadcast orbits, and they are, of course, biased because you have did not apply any offset here, but that actually confirms the size of the broadcast orbit that's applied. So again, 1 meter orbit, SLR orbit biased. And there's also a trend in the satellite and the SLR residuals for the cast-built satellites. The linear trend, we will see that also in the clock residuals on the next slide. No trend for the SCCM satellites currently. These are the clock residuals. Clock residuals means we take all the estimates and fit a linear or a second order polynomial through the residuals, basically as an indicator for orbit modeling problems. And it turned out that the cast satellites, they have a signature in the residuals. If you plot these residuals again as I did it for the SLR residuals, as a function of the Earth probe sun angle, you see again this same linear trend, which clearly indicates something is wrong here, or, well, it identifies the need for a real better radiation model, not just what we did with these two empirical terms. But it fits very nicely with the SLR residuals. That's interesting. So then we come to the SRP estimates. These are SRP estimates, again, for the cast-built satellites on the left-hand side, and for the SCCM satellites on the right. As you can immediately see, the size, the magnitude for cast is 2 times higher for the SCCM satellites. SCCM, they have recently published the size of their solar array. It's about 14 meters. So that would mean that the size of the solar array of the cast satellites must be approximately 27 meters. But there's no data available so far. We've received the properties for those satellites from the previous speaker, but would be nice to have also the area of this array. And yeah, then the variations are also not that high, only 1 to 2 nanometer per second square between high and low beta angle, and that actually matches with our expectation. If you compare these impact factors that we've seen on one of the first slides, that shows actually that there cannot be much variation in this D0 term. Then we come to the antenna offsets. So we estimated the antenna offsets based on these 11 months of data. And interesting to see here is that the cast satellites really have a quite significant offset in the X direction. I also found a figure that shows the geometry of the cast satellite. And there you also see that this antenna array with its 12 elements is clearly shifted along the x-axis and in the order of 0.3 meters. The Z offset is a bit doubtful. The values are given here for forecasts, especially the values are in green. They are in the order of 2 to up to 2.7 meters. Because the box is only 1 meter long in Z, and the offset is more than 2 meters, it's a bit weird. But on the other hand, with this graphic combination, is the question really what tells you this graphic linear combination? It's a mix of code and phase. Antenna phase center is not really a physical point, so maybe it's simply not possible to estimate it properly with this kind of data that we have right now. And what else? Yeah, the Z offset for the other type of satellites, the SSCM satellites, that matches quite well with the broadcast, this broadcast Z offset. Not so well with the recently published manufacture value, but well, that's okay. And then finally some conclusions. So we have generated first orbits and clocks for the operational BeiDou series of spacecraft. It's a very preliminary solution, as I said, just single frequency data, a small network, very, very simple orbit model, no integer ambiguity fixing. That's why the overlaps are just in the order of 1 meter RMS. But the radio component is actually quite good, 0.2 meter RMS according to SLR. We have identified some differences between the different type of satellites. The cast and SSCM built satellites are different apparently in terms of the size of the solar array. Also the space center location is slightly different. And also a really good thing is, we heard that this morning as well, the pseudorange accuracy is much better, much less noisy, no elevation dependent effects, so we probably don't need to apply these group delay corrections anymore to resolve integer ambiguities.
Thank you, Florian. Is there one important question? Otherwise, we move on. Thank you, Florian. Again. Next presentation will be given by Satoshi Hikari on precise ambient elimination of QZSS satellites with high fidelity, non-cavitation disturbance. Okay,